Professor Bob Young back at you here. And in this instructional video, Young, where do you use exponential and logarithmic equations in real life? I knew that that's what you were going to ask next as the motivated student, so we're going to look at applications and modeling in this video. So one thing, I hear a lot of psychology majors say, well, I'm never going to need math or anything, but notice, look at here, applying an exponential equation to the strength of a habit. Now, the strength of a habit is a function of the number of times the habit is repeated, you psychology majors, so you may need math after all, who knows? If n is the number of repetitions and h is the strength of the habit, all right, then according to the psychologist C.L. Hull, who you all will probably hear about in your studies, H equals, must be H for Hull, huh? The guy was famous. 1,000, it's not only mathematicians that get their name in books, also psychology people. 1,000, shut up and keep teaching young, times 1 minus e raised to the negative kn power, where k is a constant. So what we're going to do is impress our psychology folks and the psychologist C.L. Hull by solving this equation for k. All right, now what we're going to do first on this one is we go ahead and divide both sides by 1,000. So I'm going to get the colors here. So we'll go ahead here and get rid of that 1,000 in front. I think it's going to be easier to do this first than distribute it. I mean, I know some of you may have said, well, let's distribute it and do it, but it's all right. We'll go ahead and get rid of it with the chop chop. All right. Now we got to get rid of this 1 over here because we're trying to get that e by itself. So we're going to go ahead and subtract 1 from both sides, and now we're down to this step. But ladies and gentlemen, watch those signs because notice there is a minus e here, and we want to get e by itself, so we're going to divide both sides by -1 here. All right, so that will make this a positive e raised to the minus kn power, and it will change the signs on the -1 over here to +1 down on the bottom, minus the h over 1,000. Okay, now in order to get rid of the e, we're going to attack it with its inverse, the natural log. So we're going to ln both sides, and here's that rule that we have been seeing on many videos. When you take the ln of e raised to some power, oh, how many times have I written this? That power just comes what? Clean. Equals the ln of this side over here. And then to get k, we are going to divide both sides by not just n, because we want a positive k, but a negative n. All right, so to make this formula look a little cleaner, we went ahead and wrote it as -1 over n times this natural log. Because could you imagine taking this and writing it like, I mean, I guess we could have done this, a minus n down here. That looks kind of yucky with all that stuff in the top over a minus n, huh? So they just took that minus n and pulled it out since it's in the denominator in front and wrote it, and a lot of calculus people will do this too. When y'all take calculus, those of you going to higher levels always put the fraction out in front. So what do you think there? Now, once we have this formula with the final equation, if one pair of values for h and n is known, k can be found, and the equation can then be used to find either h or n for given values of the other variable. All right, so they may start measuring these things in psychological studies and go from there. All right, let's try another example here, modeling coal consumption in the U.S. Now, the table gives U.S. coal consumption in quadrillions of British thermal units, or quads, for several years. The data can be modeled with the function is defined by f of t equals 26.97 times the natural log of t minus minus 102.46, with t having to be greater than or equal to 0. So notice they've got the years 1980 to 2005 there, and the coal consumption in quads in those years. Okay. And it says where t is the number of years after 1900 and f of t is in quad. So this function is talking about the number of years following 1900. So I think what they're going to do is look at the actual consumption here and see if this function, this model up here, fits the data. So sometimes they'll do that to make up and project how much coal usage will be down the line. All right. So it says approximately what amount of coal was consumed in the United States in 2003, and how does this figure compare to the actual figure of 22.32 quads? So they're looking at 2003 here. So notice it would be going back in here, somewhere in between here. Okay. And then we're going to go ahead. Now remember, t is the number of years after 1900, right? So in 2003, that would be 103 years. So they just took 2003 minus 1900, and they put f of 103 in here and solved, and they ended up using the natural log there of 22.54. So it says based on this model, 22.54 quads were used in 2003, and this figure is very close to the actual amount of 22.32 quads. So the function looks like it fits the data pretty well. And then we can also put in 25 for t here, okay, and figure out maybe if you look down the bottom how much coal would be used, since this model seems to fit the data pretty good, approximately in 2013. All right, so looks like we're going to get here, if we put 25 in for the y or f of t and solve here, let's go ahead and go back up top. We'll go ahead first and add 102.46 to both sides. So this is just some more solving logarithmic equations, and show that you can actually use this in real life and modeling and data and so forth. And you'll get 127.46 equals 26.97 times the natural log of t. Divide both sides. And we get the natural log of t equals this fraction here. Now, to get the really good answer, we're going to go ahead and remember to solve this equation for t, the ln is base e, and we are going to do the clown face on this. We are going to say e, rewrite this as an exponent, raised to this power gives us t. And boy, this would be a good one on your calculator. If you can do this, you and your calculator are perhaps one now, you'll get about 113. So 113 years added on to the 1900 will get us that year of 2013, where the annual consumption will reach 25 quads. What do y'all think? So we can go back to the chart here. Let's see if we can find it real quick. And we have already projected using this function. We went down to 2013 and 25 quads about. So it looks like it fits it nicely. All right, so you can use this stuff in many things, psychology majors. You can use it in statistical studies and so forth, the logs and the natural logs. Be Young, signing off. Hit that homework.